As mentioned in the previous video, statistical mechanics deals with the study of ensembles of molecules, so large groups of molecules. And so in statistical mechanics, we're going to define different types of ensembles. And so the first type of ensemble that we're going to deal with is known as the microcanonical ensemble. And so these sorts of ensembles deal with systems in which internal energy, volume, and the number of molecules are held constant. Okay? So we're going to kind of go over and define a couple of terms that are related to the microcanonical ensemble. And so to do this, let's first consider a system in which we have constant internal energy, volume, and number of molecules. One example of such type of system would be something that we've already seen, a two-state system, right? Where you're either in box A or box B, or a particle is either in the ground state or in some excited state. Something simple like that. And if you recall, when we discussed the two-state system, and we're trying to describe the probability that a particle is in one state versus another, we invoked what's known as the principle of a priori probabilities. And so just as a refresher, all this said was that the probability of a particular microstate would be described like this, where the probability would be equal to 1 over omega at an internal energy sub m, which is the internal energy of that microstate, at some volume, at some number of molecules, if that um, the internal energy of that microstate, is equal to the internal energy of the observed macrostate. Okay? All right, and so if the internal energy of a microstate is equal to the internal energy of the observed macrostate, then the probability we see that macrostate would just be 1 over the omega for all microstates that correspond to this macrostate energy. For microstates in which the energy is not equal to the macrostate u, then the probability of observing it was 0. Right, that's what the principle of a priori probabilities said. And so, in a compact way, we could describe this probability like this, where we have our delta function, u over omega u v n, right? So this is just a compact way of describing this sort of binary choice here. Okay? All right, so the probability is equal to this. And we know if we sum up the probabilities, that the total sum of all of the probabilities needs to be equal to 1. Okay? If we're summing up P of m, we could plug this in here. So we have this okay? All right. So we just plugged in for P of m, and we have this summation. And if we look in the denominator, here, this is just the macrostate internal energy, right? So our summation here is a function of m, but this is independent of m. And so what we could do is, since we know that this is equal to 1, we could just move this denominator to the other side. And what we get is that omega u v n is just equal to the summation of our delta functions. Okay? All right. And so from the principle of a priori probabilities, we could get this sort of relationship, which just says the total number of microstates in our system is equal to the summation of this delta function. Right? So I just wanted to remind you of these sort of definitions, because when it comes to statistical mechanics, if we're dealing statistical mechanics, if we're dealing with a system in which internal energy, volume, and the number of molecules are kept constant, then we typically refer to that system as a microcanonical ensemble. So microcanonical ensemble. All right. So, it's a sort of fancy term that basically just says that we're keeping U, V, and N constant. And when we're dealing with microcanonical ensembles, there's going to be a partition function associated with that. Okay? And so if you recall from Module 5, that's where we introduce the concept of partition functions. Right? And the whole point of a partition function, it was just a mathematical concept in which, or a mathematical function that just normalizes the probability, so that when we sum the probabilities up, they equal 1. Okay? And so here, we're summing our probabilities up, and in order to get it to equal 1, we see that we are dividing it by this omega, the density of states, the number of microstates. And so by definition, just based on this relationship, we see that for the microcanonical ensemble, that by definition, its partition function is just omega. Okay? All right? And so when you're doing a microcanonical ensemble calculation, the partition function that you want to calculate, which describes, not only normalizes the probability, probability values, but also basically describes all of the possible configurations that the system can achieve. Right? That's just going to be omega. Okay? Now this omega is useful for thermodynamics because we know that by definition the entropy is just kb ln of omega. All right? And so what that means is for microcanonical ensembles, the main sort of driving force in these systems is the goal of maximizing entropy. So maximizing entropy is the main driving force. Okay? All right? And so here, the thermodynamic potential of interest that we're going to be dealing with in microcanonical ensembles is the internal energy. So U is the thermodynamic potential of interest. Okay? All right, and so to summarize, the microcanonical ensemble is just a system in which internal energy, volume, and number of molecules is kept constant. The associated partition function is just omega. In these sorts of ensembles, the main driving force for achieving equilibrium is maximizing entropy. and the internal energy is the thermodynamic potential of interest.